Okay, this is our second video from Chapter 11, where we are talking about simple harmonic oscillation. And I've already made a few references to potential versus kinetic energy in our simple harmonic oscillator. So if we recall, the potential energy, the elastic potential energy stored in a spring is equal to 1/2 kx squared, where x is the distance that the spring has been either stretched or compressed from its relaxed position. So at any point in time in the motion of our simple harmonic oscillator, we could calculate how much potential energy is stored within the spring. The total mechanical energy, therefore, is going to be equal to the sum of the kinetic energy of the box that's moving back and forth, which is 1/2 mv squared, and the potential energy stored in the spring, which is 1/2 kx squared. So energy is conserved. There's no energy being created or lost in this system. So at any given point in time, we could find the total amount of energy by summing these two types of energy, the kinetic and potential energy. Now, there are certain points in the motion of our simple harmonic oscillator where it's a lot easier to calculate. For instance, it's easiest to calculate the amount of energy when it's either all stored up in the spring. So when the box is all the way to the left here at its negative amplitude, the box for a split second comes to rest, and all of the energy is stored in the spring. So it's 100% potential energy at that point. Then as the spring stretches back out, for the split second, it passes past this point. For just a split second in time, the spring is completely relaxed, and therefore all of the energy is in the form of the box moving. So at this point, it's 100% kinetic energy. And then it passes past that point and reaches eventually its extreme positive amplitude. Again, when it gets to that point, for a split second, this box is going to come to a stop before it changes directions. And when that occurs and the box is motionless and the spring is completely stretched out, again, we have 100% potential energy stored in the spring. So these points are where it's easiest to calculate the total amount of energy in the system, when it's either 100% potential or 100% kinetic. At every other point in time, where the box is somewhere in between the point where the spring is relaxed or completely stretched out at some other random position x, then the energy is going to be a combination of both potential and kinetic energy. And at these points, it becomes more difficult to calculate because we don't know what exactly is the velocity of the box at that point in time. So it's easiest if we can choose what point, what position to investigate. It's much easier to choose either completely potential or completely kinetic. So this 1/2 k a squared, a is the amplitude, which is where the system is completely stretched out. So if I back up to this slide, so for instance right here, where it's stretched out to its fullest point, the total energy in the system is all potential. The distance x that's stretched out is actually a, the amplitude, so it's 1/2 k a squared. Or up here, for instance, where the spring is completely compressed. Again, it's at its negative amplitude, so the total energy at that point is 1/2 k a squared. So looking at these points where it's 100% compressed or 100% stretched out, and all of the energy is potential, that's a good point to calculate the total energy in the system. So all we're saying here is that the sum of the kinetic energy and the potential energy is equal to the total energy, and the total energy is 1/2 Ka squared. Okay, so if we take this as a given, and we wanted to solve for V, as I mentioned earlier, it can be difficult to calculate the energy in the system when the box is somewhere in between its resting point and extreme amplitude point, because we don't know what the velocity is. Well, velocity is the unknown variable here, so if we solve for it, we can find that the velocity is equal to plus or minus the maximum velocity times the square root of 1 minus x squared over a squared. Well, that's great, but what is the maximum velocity? Well, again, based on this equation up here, we can derive this formula down here for maximum velocity. The maximum velocity, which comes from the total amount of energy in the system, if we calculate that for velocity when the box is 100% kinetic, then it's equal to the square root of k over m times the amplitude. So if we wanted to calculate the kinetic energy at some point in between the point where the spring is at rest or fully stretched out, we would first need to calculate the maximum velocity, take this, plug it into here, then this would give us the velocity, which we could then plug into this equation, and we could calculate the energy at any other given point in time. It's simpler, though, if we're just interested in finding the total amount of energy, to investigate the position where the box and the spring is stretched out to its amplitude. All right, let's look at another problem here involving springs. Example 11.4, where we have a spring that has been stretched 0.150 meters. So our distance here, 0.150 meters, is how much the spring is stretched out when a mass of 3 kilograms is gently suspended from it. So 3.00 kilograms. What is the spring constant? Let's move on to the next slide here to give us some room. So the spring constant, K, is equal to the force divided by X. And that comes from Robert Hooke's equation that the force required to stretch out a spring is equal to K times X. So if we solve for K, it's equal to the force divided by X. Force is equal to mg, and the mass of the weight was 0.300 kilograms. The acceleration due to gravity is 9.8 meters per second squared. And the distance the spring stretched out in this example was 0.150 meters. And so calculate that out, and it looks like our spring has a spring constant of 19.6 newtons per meter. Okay, so that's just sort of, again, a little bit of a review of dealing with springs and spring constants. Let's now take a look at this situation where we set it up horizontally as a simple harmonic oscillator. So we calculated the K value, it's 19.6. So we can write that down, K equals 19.6 Newton per meter. That's we're going to need to know that in order to investigate this simple harmonic oscillator. So the mass of the box, again, is going to be still the same 0.300 kilogram. We're going to pull it and stretch it out 0.100 meters and then release it. So that's going to be the amplitude. The amplitude that we stretch this out is going to be 0.100 meters. And then we're going to let it go, and the box is going to oscillate back and forth. And assuming zero friction, it's just going to keep going. We want to know what is the amplitude. Well, there we go. That wasn't hard. And what is the maximum velocity? So let's just move on to the next slide here. So again, amplitude, that's kind of given in the problem statement. The amount that we stretch it out to start the motion of the box, that's as far as it's ever going to get. So that is the amplitude, 0.100 meters. So that's the answer to the first part of the question. The next part of the question wants to know what is the maximum velocity. So when we let this box go and it gets back to the point here where the spring is at its relaxed position, that's where the box is going to be moving its fastest. And if we want to know what that is, well, we just introduced that equation a few slides ago. That's equal to the amplitude times the square root of k over m. So if our amplitude is 0.100, k, we calculated that in the first part of this problem. That was 19.6. And the mass of the box is 0.300. Okay, so the maximum velocity is 0.100 times the square root of 19.6 divided by 0.300, and that should work out to be 0.808 meters per second. That's the maximum velocity that the box is going to have at the point where the spring is in its relaxed position. Okay, so I don't have the problem statement written here, but part D of this question wants to know the velocity. What is the velocity when the mass is 0.05 meters from equilibrium? So in other words, x is going to be 0.05 meters. And then part E of the question wants to know what is the maximum acceleration of the mass? Acceleration max. What's that? Yeah, let's find out. So the velocity at any point in this oscillation can be found by the equation Vmax times the square root of 1 minus x squared over the amplitude squared. So we calculated our maximum velocity to be 0.808 meters per second. We're going to multiply that by the square root of 1 minus, we want to know when x is at 0.05 meters. Square that, divided by the amplitude, which was 0.300 squared. Okay, hold on. I just realized what I have in my notes is right here. This is the mass, and we want the amplitude. The amplitude is 0.100 squared. So let's fix that. And so when we take 0.808 times the square root of 1 minus 0.05 squared over 0.100 squared, that should come up with a velocity of 0.700 meters per second. So that is the velocity at the point where it's 0.05 meters away from the relaxed point. And it looks like I'm not going to completely finish this example problem. I'm about to run out of time, so I'm going to pause the video here and finish this in the next video.